subject in this context, and it's a challenge, and there are a lot of interesting features to it. The bottom line is that if my guesses are right, it's not an issue of computer power. The amount of computer power that you would need to do it right, it would be tens of orders of magnitude or more bigger than what we've got. I mean, picking up a factor of 1 order of magnitude or 2 or 3 in computer power won't hardly begin to cut the problem. And so it's just not feasible to do the job if my concerns are right. It's not just my concerns, the concerns that were first raised by other people, particularly Bernard Schutz. And then after that, Jan 11. So let me explain what my concerns are. In order to explain my concerns, I need to talk about the orbits of small objects, neutron stars, white dwarfs, small black holes around a supermassive black hole. Now, I want to work my way up in this discussion. Let's suppose that the gravitational field were Newtonian. Then we know that the orbit would be an ellipse, with the big black hole at one of the foci of the ellipse. The orbits are expected typically to have rather high eccentricity because, as Sturl discussed, the way in which you get the small object into the vicinity of the black hole is by scattering it into the loss cone when it's sitting out at some relatively large radii and has a near encounter with some other star. It gets scattered into the loss cone, which means basically it gets scattered so it's headed almost radially at the black hole. And so it's out here in some orbit like that. But there are a lot of other stars out there. There's a near encounter, and this guy gets sent down in. And then gravitational radiation starts doing its thing, and the orbit starts shrinking. The apastron, of the upper point of the orbit, starts shrinking down the lower and hardly changes at all. And so you would wind up then with actually, we expect, rather eccentric orbits when you go through the details. And they would be ellipses in Newtonian theory. When you look at the effects of general relativity, but a non-spinning hole you find what relativity does is produces a Periastron shift, like the perihelion shift of Mercury. And that arises because the period for angular motion becomes shorter than the period for radial motion. And so if you have your orbiting object out here, it heads in and comes back out. But by the time it has finished its angular motion through an angle of 360 degrees, it's not yet finished with a radial motion. And so it finishes the radial motion out here after it has advanced in its periastron and in its apastron, after it's advanced through some angle. And as you might expect, the closer the inner part of this orbit is to the black hole, the larger is going to be this periastron advance. And so as this orbit shrinks, initially what you have is something comes in like that, has a modest periastron advance, and you get a waveform like the one I'm going to show you. So these waveforms were computed by Dan Kennefick and Kostas Glampadakis. Dan is one of the editors on the Einstein papers here at Caltech, but he spends 20% of his time doing gravitational wave related research. He's both a physicist and a historian of science. And he and Glampadakis, who is a graduate student in Cardiff, Wales, have been solving some equations that I'll talk about just a little bit in a few minutes to compute these waveforms. And what you see here is the waves from the epoch when the small black hole is going out and coming back in, very slowly changing amplitude. And then when it comes in and swings around the big black hole, you get a spike. And so we would expect, in fact, that in typical cases, except in near the end, you'll wind up with waveforms that are quite spiky like this, very quiet, and then you have a big spike with some unknown, well, to be determined, to be measured interval between the spikes. Now,
what are the irregular ripples?
What
are the small ripples?
The small ripples are numerical error due to an artifact of how the calculations are done. Okay, so now when the small black hole gets closer to the big black hole, closer to the horizon, the amount of the Periastron Shift gets larger until ultimately you wind up with an orbit where it comes in, it actually goes around a number of times, then goes back out. Comes in, goes around a number of times, then goes back out, and so forth. The reason for this is tied up in the effective potential for radial motion. If you use angular momentum conservation for geodesic orbits, I'm not talking about in spiral right now, just imagine it has a geodesic orbit. Use angular momentum conservation like you would in Newtonian theory. In Newtonian theory, you would wind up with an equation that says that dr dt for the radial motion is equal to minus m over r plus L squared minus 2m over r plus L squared over r. Is it L squared over r squared? L squared over r squared. And this is, and so the thing on the right-hand side is basically an effective potential. You might write that as 1/2. So this is the kinetic energy per unit mass. You get rid of this 2. You have a 2 down there. Then you can recognize this as kinetic energy per unit mass. And there's a potential energy term. I'm sorry. Let me write it plus this is equal to the total energy. So kinetic energy per unit mass plus gravitational potential energy per unit mass. This is the radial part of the kinetic energy, and that's the angular part of the kinetic energy using angular momentum conservation. And you call this thing V of R, and that's an effective potential that includes a centrifugal potential piece and a gravitational potential piece. And you draw a graph then of V as a function of R, and this is, say, 0 here, and it goes down, and then it rises due to the centrifugal potential. Now in relativity, you can do the same thing, but instead of dr dt, it's convenient to write dr d tau, or tau is proper time, plus a v of r is equal to E, and the V of R that you wind up with, and I won't write down the formula, but the V of R that you wind up with has this kind of a form, and then it turns over. And this lies behind the discussion that Alessandra gave for binary black hole systems of what happens with the in-spiral as the system emits gravitational waves, it loses angular momentum, so the centrifugal term becomes weaker. And so this potential then looks like that as the centrifugal term becomes weaker. And then like that. And well, I'm not going to. And Alessandra showed the orbit for circular orbits going down like this to smaller and smaller radii, and finally reaching the ISCO down here. So that lies behind what Alessandra was talking about last week. But now if we talk about radial motion, we have a given amount of energy. We were in a highly elliptical orbit. What happens is that the radial motion, of course, is a motion back and forth from an apastron to a periastron back and forth. And then after you've lost some angular momentum and lost some energy, you may be moving back and forth like this. And here, because the potential is nearly flat, is becoming very flat, and you're near the peak of the potential, you linger for a long time in here. Lingering for a long time in here means that you are able to go around and around a number of times at small radii. And then soon after this, the small object begins its plunge. So it has to do with the nature of this effective potential and the effect of general relativity on it in turning, in overcoming very near the black hole horizon and overcoming the centrifugal barrier. Okay.
How can you see from the spot that it's spending a lot of time in the radius?
So if you were to wind up right on the top of here, you're sitting there at fixed radius with dr dt squared vanishing, but you still have some finite L squared because this term is still present, counteracting the effects of general relativity, which are trying to push everything in. The fact that you still have some angular momentum means you're still moving in angular motion.
So I guess my understanding of it now is that you can see that the dr dt is getting very small,
Yeah.
close to that,
Right.
That maximum.
Right.
And so if dr dt is small, it means
That's right. So dr dt is 0 if you're sitting at the top of the maximum. But the d phi dt is still finite because L is still finite. If L were not finite, you'd be plunging directly radially in. Okay, so the question is then, what does the orbit look like in this case? In this case, this is called a zoom whirl orbit. You zoom out and you go in and whirl around, and you zoom out and go in and whirl around. So for a zoom whirl orbit, what do the waveforms look like? And these are, again, Dan Kenefic's calculations. These are actually calculations not in the Schwarzschild geometry, but for a Kerr black hole, or rather rapidly spinning Kerr black hole. I think it's probably 0.99, but I'm not sure. And this is not a terribly elliptical orbit, but what's going on here is this is the zoom part, relatively low amplitude, and a large period. You get actually two peaks. One peak is when the waves are, when the object is basically moving toward you, and another when it's basically moving away from you. And they have different heights because there's a breaking of the symmetry between toward and away. But approximately the same height. And then the whirl, you have a number of cycles. And then the zoom, then the whirl, a number of cycles. Okay. And it can become much more extreme than this. This is not a very elliptical orbit. Kenefic and Glampadakis have been having trouble doing their calculations when you become highly elliptical. And so they don't deal with eccentricities any larger than about 0.8. But in the extreme case, you would have a much longer and more gentle zoom part of the signal. Now, thus far, I've talked only about radial and angular motion. But in the case where you have, a Kerr black hole, and the orbit is not in the equatorial plane, so the black hole is spinning like this, and the orbit is like that. The spin drags inertial frames, and so the orbit precesses. And so we've already looked at that, and we know that what that will give then is the orbit precesses, we see a modulation of the waveform. And so you see the amplitude modulated, and you see the phase of the wave modulated. When the orbit gets down to close to plunge, it gets down in here really quite close, and is going around a number of times. In this case, the dragging of inertial frames is so strong that, in fact, the orbit really has a motion in the phi direction that has a period for the phi motion that is very much shorter than the period for the theta motion. This frame dragging dominates, and instead of merely having a modulation, the frame dragging is a bigger effect than the theta motion up and down. So the orbit looks sort of like an electron orbit spiraling in the Van Allen belts of the Earth, back and forth between mirror points. Not an extreme version of that, but sort of like this. So it goes up and down, a few orbits around for every time it goes up and down. And when you superimpose this motion on the elliptical motion and the effects that you get with the elliptical motion, you get a very complicated motion. You've got zoom whirl behavior, you've got this up and down behavior, and as you can imagine, the waveform becomes very complex. And in order to cover the whole family of waveforms that you might actually see in practice, it will take an enormous number of theoretical templates to be able to do optimal signal processing for all these waveforms. And a fundamental issue is how many. Is it 10 to the 6? Is it 10 to the 16? Is it 10 to the 26? We don't know. And we don't know at basically that level at the moment. And so that is one of the key issues that has to be sorted out, is just a piece of figuring out how badly we're going to lose relative to optimal signal processing. Now you might ask, how does one compute the waves from this orbiting object? And I'll just say what one uses is something that is called the Tucholsky formalism. The Tucholsky formalism is the theory of first-order perturbations of the geometry, the space-time geometry of a spinning black hole. And so Saul Tucholsky, when he was a graduate student here in 1972, he devised this formalism as a mathematical tour de force. And this has become the standard tool for doing any kind of a study of gravitational perturbations of black holes. And when you have a small mass ratio, a small mass object spiraling into a very massive black hole, this is the way to do the calculation. And so it really is a first-order perturbation theory calculation, so you might think it's very easy. It's not. It's not easy at all. It's very complicated. And so the waveforms that I showed you just for equatorial orbits, so that Glampedakis and Kennefic have been building, they're based on, I guess, 4-person years of work by these guys, just to be able to build these kinds of waveforms in that case. And so it is a major computational task, but we know how to do it, and that's the key thing. We do know how to do this part of the problem. Okay, so are there any questions about this? We will return to this issue when we talk about signal processing next term. And there are a number of interesting issues then that dovetail, come in, and are closely connected with everything I've said. But I want, in the last 15 minutes, to talk about gravitational waves from the very early universe. As you can see, we're trying to go through, at some level of detail, a little bit of level of detail, all the major sources of gravitational waves for LIGO and LISA. And they're the international partners of LIGO. So what I want to do is describe for you just a little bit of the mathematics that underlies the fact that one can begin at the Big Bang in the very early universe with nothing except vacuum fluctuations of the graviton field, treated quantum mechanically, if you wish. And one can wind up with strong gravitational waves today through a process that classically would be parametric amplification of the gravitational waves. In quantum gravity theory, perturbative quantum gravity theory, it would just be graviton production, so particle creation. And so I'm going to just sketch out how this goes. It's really rather simple. And so what we have is a gravitational wave that is propagating on a background space-time. The background metric, even today we know the universe is very nearly flat spatially. And in the early universe it should have been even more flat spatially. So I'll take the background metric to be minus dt squared plus an expansion factor that depends on time. And let me use Cartesian coordinates, dx squared plus dy squared plus dz squared. And in order to make the mathematics simple, it's useful to introduce an alternative time coordinate defined by d eta is equal to dt over a of t. And so you just integrate this up to get eta as a function of t. And if you do that, then the line element just becomes, as you easily see, minus a squared of eta times plus a squared of eta times minus d eta squared plus dx squared plus dy squared plus dz squared. And of course, a, the expansion factor of the universe, is something that increases in some manner that may change as the universe evolves, with a very rapid early inflationary epoch, a very rapid expansion, and a slower epoch of expansion today, which is now accelerating a little bit, the observations tell us. Now, on top of this space-time geometry of the expanding universe, we have gravitational waves. And let me have these gravitational waves propagate in the z direction and have the plus polarization. So h plus is hxx is minus hyy. These are the only components. And when the waves, or in the modern epoch, when these really are waves, and I will tell you that they were not waves in the very early universe, at least for part of the very early universe. In the modern epoch, this is going to have the form of some constant over the cross-sectional area of a bundle of rays that are all propagating in the z direction. And it'll be e to the I kappa z minus eta. Why z minus eta? Well, you can just see if it's propagating in the z direction, z minus, and it's propagating at the speed of light, ds squared is equal to 0 if dz is equal to d eta. So something that is a function of z minus eta is propagating at the speed of light, because the metric has the form of some factor out in front, and then it's just a flat space metric. And this factor out in front is common to the z and to the eta. And so this would be propagating at the speed of the light in flat space, and that common factor out in front doesn't change it, because you have the d eta here and the dz there. Now the cross-sectional area of a bundle of rays, these rays are all propagating in the z direction. They don't have any changing x or y along them, and so their cross-sectional area is just proportional to a squared, the expansion factor of the universe, because that's just measuring how much expansion there is in all three directions. So along the x direction, the universe expands proportional to a, along the y direction proportional to a, and so the cross-sectional area of a bundle goes as a squared. So the square root of a of that cross-sectional area is just proportional to little a. And so I can write this gravitational wave field then as some constant, I'll call it mu, over little a, e to the, let me write it, e to the minus I times kappa times eta, then e to the I kappa z. This is true at late times. In the geometric optics limit. Now, by late times, I mean when the measured wavelength of the waves is small compared to the radius of curvature of space-time. That's what we need for the geometric optics limit. But in the very early universe, the radius of curvature of space-time gets very, very small. And so and it may get smaller than the wavelength of the waves. And if that happens, then we can no longer have geometric optics waves, and this, which is basically a geometric optics solution, will fail. And so in the very early universe, we have to look for a solution that will become of this form as you go into the later universe. If you look at the first order, at the Einstein equations for these first order perturbations of that metric, you discover, perhaps not surprisingly because of this form that you have in here, you discover that you can do separation of variables on the metric perturbation. And so you can write H plus as a product of some function of eta times some function of z. And because the metric has no dependence on z at all, we are guaranteed that you can write this function of z as an e to the I kappa z. When the metric has no z dependence, then you can just do an ordinary Fourier analysis, and you're guaranteed that that will be the basis for a solution of your equations. So I'm just telling you some things. Okay? So you do separation of variables, and the z part then retains its same form, unchanged, but the eta part, because the metric depends on eta through the expansion factor, it will not retain this form. But I can write it in this form if I just let mu be some function of eta. And so I'm going to write H plus is mu of eta divided by a of eta, e to the minus I kappa eta, e to the I kappa z at all times. You then go in and you look at the Einstein equation and see what do the Einstein equations say about the function mu of eta. The Einstein equations become really quite simple in terms of mu of eta. They just say that mu comma eta, two eta time derivatives, plus kappa squared minus a comma eta over a times mu is equal to 0. So that's the Einstein field equations at first order. If this a term were absent, this would just be two time derivatives on mu plus kappa squared times mu is equal to 0. And the solution would be, oops, just a second. What I want to do is, I want to turn this whole thing into mu of eta. So, okay, so let me just think about how best to do that. Let me call this lambda of eta. So I've absorbed the e to the minus I k eta into there. Okay, so lambda of eta times this. So lambda becomes mu e to the minus I k eta in the geometric optics limit. Okay, and this equation is lambda comma eta and lambda. And the statement is if, let me call this quantity here v of eta, it's some function of eta. And my statement is if v of eta is very small compared to kappa squared, then this has a very simple solution. Lambda is equal to e to the minus I kappa eta, or e to the plus I kappa eta, times some constant. So times some constant mu. And that is the solution that I began with at late times. So that's late times. On the other hand, if v of eta is large compared to kappa squared, then I can ignore the kappa squared term, and I can actually solve this analytically for eta, for lambda again. Then I wind up with lambda is equal to either a constant mu, so it's, or there are two solutions. The second solution is some constant, say k, or say c, times the integral of d eta over a squared. So, right? Or mu is a constant times a. It's a constant times a. Lambda is a constant times a, or it's a constant times a times the integral of d eta over a squared. Now, when a is increasing rapidly, as in the early universe, this thing goes to 0 with increasing a. And so this solution basically dies out. It may have been present in the very early universe, but it dies out. And this is the solution that we get. Lambda is mu times a when this potential term dominates. Lambda oscillates sinusoidally when the potential term is negligible. Now, this potential term is really radius of curvature of the universe, or one over the radius of curvature, basically squared of the universe. And what's happening is that when this term is large, you've lost the geometric optics limit, and these waves are no longer waves. They are being grabbed by the curvature of the universe, and they're being held in some manner. In what manner are they being held? They're being held in such a way that lambda is proportional to a, but since h is lambda over a, that means that h is frozen. H is a constant times e to the I kappa z. And so that corresponds to h is equal to a constant e to the I kappa z when the geometric optics approximation fails. When the geometric optics approximation is good, then you have this oscillating solution that I began with. Okay. So now what I need to tell you is how does this radius of curvature term of the universe behave as a function of eta. And I will just tell you that for standard cosmological models, standard meaning standard inflation of the universe at very early times, you have during inflation, this V rises. Then when inflation ends, it drops to 0 for a while, and then it rises back up and falls. This era is the era in which the radiation density associated with a cosmic microwave background is small compared to the matter density. So this is that occurs at a redshift of about 1,000 or a few thousand, 3,000. And this is the era in which the radiation density is large compared to the matter density. And this is the inflationary era. Now the key point is that the behavior of the amplitude of the waves is such that the amplitude of the waves are dying out as 1 over, or let me start over again. Let me plot across here kappa squared. So in the very early universe, the kappa squared dominates and you have waves. They're oscillating along, and they may be nothing more than vacuum fluctuations that came off the Big Bang, off the Planck era. At this point, the words that people use is that these waves exit through the horizon of the universe. These are the words that are used. Let's not worry about what they really mean. And now the waves become trapped. In here, h is dying out as 1 over a. When they're trapped, h is constant in terms of its amplitude. And then they start dying out as 1 over a again, out here. So a little complication due to this gap, which I don't want to go into the details of. The key thing is that when you have true waves at the very beginning of the universe, that may be nothing more than vacuum fluctuations, h is dying out as 1 over a. It's dying. But gravitons are conserved. If you begin with half a graviton per mode of the graviton field, which is what you would have according to quantum mechanics in the vacuum, you just conserve the number of gravitons. We know in the geometric optics limit, gravitons are conserved. But if you have the amplitude of the waves fixed, but the frequency is continuing to die, instead of the amplitude going down as 1 over a, you're producing lots of gravitons in here. At fixed amplitude, with decreasing frequency, you're producing lots of gravitons. You come out of here with huge numbers of gravitons, and gravitons now are conserved again. And so the inflationary period actually creates gravitons, or classically, what we say is there's a parametric amplification of the initial gravitons to get lots more gravitons in a manner that corresponds to parametric oscillators. And it is this process, in fact, by operating not just on gravitational wave field, but on all other fields, that is believed to give rise to the perturbations of density of matter from which galaxies form, beginning with nothing but vacuum fluctuations at the very beginning, and then amplifying other fields by just this analogous process to get fluctuations at just the right level to form galaxies. And on the graviton field, you begin with vacuum fluctuations of the graviton field. Then the amplitudes are frozen in this inflationary epoch. Number of gravitons is increasing, and then you have a big rich graviton field that, according to standard inflation, is not strong enough for us to detect with LIGO and LISA, but could very well be strong enough to see in the cosmic microwave background. We'll discuss that detection issue next term. Okay. So on next Monday, then Lee Lindblom will talk.